Hello everyone, in this presentation we will discuss making a purchase decision of medical imaging equipment for a local hospital. Making a purchase decision for medical devices is usually the responsibility of biomedical engineers. Because different hospitals have different needs, this decision requires some analysis of different factors, including how many people visit the hospital, the level of healthcare provided by the hospital. For example, highly specialized healthcare centers require more sophisticated specialized devices. The goal of this project is to analyze and select medical imaging devices based on certain specifications given by the hospital. The devices that we will discuss today are ultrasound machines, MRI machines, and X-ray machines.
Ultrasound is an imaging tool or an imaging modality that is used to scan or image different parts of the body. It can be used as a diagnostic tool or a therapeutic tool in some applications. In this case, we look at a general purpose diagnostic ultrasound. Ultrasound works on the principle of measuring ultrasonic waves travel time as they travel through the body. The speed of ultrasonic waves differs through the different tissue caused by the different tissue impedances. This difference causes the ultrasonic waves to also get reflected back to the transducer, and also some of them will get absorbed by the tissue itself. The transducer then measures the travel time of the reflected back ultrasound, and then it can estimate the location of the reflection, and thus it can draw a 2D or in some cases a 3D image of the sector inside the human body. Some of the important specifications of ultrasound and its hospital requirements based on that are the basic application of the ultrasonic device itself. In this case, we look at the general purpose ultrasounds for abdominal cardiology and gynecology application, as different devices are specified towards specific applications, such as vascular imaging and so on. We also look at the available probes that come with the device. These usually include the three main probes, such as the linear array, the convex array, and phased array. We also look at the frequency range of those probes. Some devices have a limited frequency range, a specified frequency range such as 2 megahertz. Others include the multi-frequency option, which includes the full spectrum of the specified frequency. We also look at the different imaging modes, including the basic brightness mode and then the M mode imaging, which is movie mode imaging. We also look at the available Doppler modes. These must include continuous wave Doppler, power Doppler, duplex or frequency Doppler, and then color flow Doppler, and then power Doppler. We also look at some of the required or necessary features, such as the dynamic range, the selectivity of the dynamic range to differentiate different tissues at different levels. We also have the transmit and receive dynamic focusing. We also look some of the image features, such as real-time imaging and freeze image feature, and then some available analysis programs that are pre-configured in the device, such as a cardiac program, a vascular, and gynecology program. We also look at the available grayscale in the screens. Typically they are 265. Some screens offer more, but this is usually the available. Also, the power requirements for the hospital, which is 110 or 220 volt AC. After identifying all of the important specifications and the hospital requirement, we generate a specific tender document for the vendors that includes all the necessary specifications for the device, and based on that we get our different devices to compare with, which are the ProSound Alpha 10, the UF870AG, and the Sonace X8. Different manufacturers and different devices. Now we compare them based on our specifications, and we can see that the Sonace X8 is the most fitting device for this application. Also, while the other devices might lack in Doppler modes and the general application of the ultrasound itself. Now we select the final selection for our device with the primary device being the Medsun Sono-Ace X8 and two available backup devices, which are the Fukuda Denshi UF870AG, and then for the secondary one, which is the Aloka ProSound Alpha 10.
MRI or magnetic resonance imaging is basically a hydrogen distribution map, although it can be a map of different atoms for different applications, but the most common one is hydrogen. The basic idea of MRI machines are, first of all, a magnetic field is applied, making the protons or the hydrogen atoms act as a radio station. And then a radio frequency pulse is sent at a certain frequency called the Larmor frequency, which is determined by the magnetic field strength and a constant that is different for each atom. After sending that energy, the protons store that energy, and then when the RF pulse is turned off, that energy is sent back, and then we can measure that energy to find out how many hydrogen atoms are there. And then something called spatial encoding can be used to determine the position of different signals. This is a list of the selected specifications with an explanation and a justification for each one. First of all, starting with the clinical applications, some MRI machines are only for certain regions of the body, but it's best to have a general MRI for the whole body. For the magnet strength, higher magnet strength means having a better signal-to-noise ratio at the cost of having a larger fringe field. We chose 1.5 Tesla because it's a good middle ground between a good signal-to-noise ratio and not too large of a fringe field. For the magnet homogeneity, this is a level of uniformity of magnetic field. Low homogeneity means having low resolution images and it might have some distortions. For shielding is used to reduce the extent of fringe fields. There are three types. There can be no shielding, passive shielding, and active shielding. We chose active shielding because it reduces how far the fringe field reaches the most. Bore diameter, this is the height of the patient opening. A larger opening accommodates a larger patient, and it might also reduce the effects of claustrophobia. For the image processor maximum matrix size, this is the maximum matrix size that can be supported by the image processor. Having a large matrix contributes to a higher resolution. The extent of the fringe field is the distance to the 5 Gauss line. Anything below 5 Gauss is considered safe. For the minimum ceiling height, this is the minimum ceiling height for a room to accommodate the MRI system. For the peak sound pressure levels, this is the peak sound pressure at the maximum gradient, amplitude, and slew rate. While wearing a headset, things at 30 decibels or even 40 decibels should be fine for the patient. And because 120 decibels is the threshold of pain, we wanted the MRI machines to be less than that at 100 decibels. For the standard slew rate, this determines how fast the gradient system is. Faster systems produce higher resolution images, and it also reduces the time of acquisition, which might help in reducing the chance of movement. For the DICOM standard, this is a standard that allows devices from different manufacturers to communicate. We want this to be supported for future proofing, so that if the hospital buys a device from a different manufacturer, data can be transferred between the devices. This is a tender document containing all the specifications that we can send to the vendors. Here we compare some MRI devices from different manufacturers. First we have the Oasis from Hitachi, the Achieva from Philips, and the XLR from Toshiba. First of all, for the Oasis, the magnet strength was too weak, the bore diameter was too small, or the bore was too small, and the extent of fringe field was too high, and it had very high sound pressure levels. It also, its slew rate was way too slow. For the Philips, it satisfied almost all the conditions. It was a little bit too slow though. For the Toshiba MRI machine, it satisfied all the conditions. These are our final selections for the devices. First, the primary device is the Toshiba one, the XLR, because it satisfied most of the conditions. The first backup is the Philips one, the Achiever, and finally the second backup is the Hitachi Oasis.
X-ray machine. X-ray is a high-energy electromagnetic radiation produced using a high-voltage source, which accelerate electrons and make these electrons go through the body or target some objective such as tissue to produce an image of that tissue or objective. X-ray radiations are painless when passing through the body and used for diagnostic or therapeutic purposes. The X-ray is usually used to diagnose a disease or problems in the bones or joint in the body. These are the specifications and hospital requirements of the X-ray machine. So for the specification, first clinical application. Either the X-ray machine is for general application or for specific application. And since there are many patients in different situations visit the hospital, it's better to have general X-ray application to cover a wide range of patients. System type, either system is fixed room or mobile system. And in case of the hospital, the fixed machine or fixed X-ray machine is more functional and powerful. Besides, the patient can't go for the X-ray and no need for the mobile X-ray. Power, the power required to operate the X-ray machine. And since the hospital machines and equipment operating in almost in 220 voltage, it's better to find an X-ray machine operating near to this value. Throughput is the number of images that the machine can produce every 1 hour, and since there are many patients visit the hospital every day, it is helpful to produce a suitable number of images in a suitable time, and also serve many patients in a good time. Detector imaging size, the size of the detector that detects the signal or radiation that coming back from the body. The size of the detector is playing an important role of image size and image efficiency. Pixels, the pixels of the image. The pixels of the image are important to produce clear image and decided the resolution of the image. kV range or kilo voltage range, the voltage used by the tube to produce the suitable amount of radiation. And in case of the hospital, since there are many patients visit the hospital, it's better to have a suitable amount of kilo voltage range that can reach thick bodies. Table dimensions, the dimension of the table that the patient will lie on, and it's better to have a suitable or a convenient size table size to cover different sizes of the patients. Patient load, the weight that the table can load. Also, it is better to have a table that could load a high weight patients. This is the suggested vendor specification list of the X-ray machine. For the specification, the clinical application is better to have a general X-ray machine application. System type is fixed room machine. Power is up to 240 voltage. Throughput is about 100 images per hour. Detector size is 35 by 43 centimeter or more. Pixels 100 40 micrometer or more, kilovoltage range up to 100 kilovolt at least. Table dimension 135 by 64 or more, or any table that have the same area or more. Patient load 300 kilogram or more. Here we are comparing three different X-rays machine, which are Dell Medical FWFC, Siemens Multi-Impact C, and Philips Healthcare Digital Diagnostic C90. For the clinical application, we can see that all the three machines are for the general purposes, and the system type is fixed room for the L. For the power, we can see the Dell Medical FWFC is operating in a voltage around 230, and for the Siemens machine is as the hospital require, and for the Philips is either 115 or 230 volt. For the throughput, we can see the Dell Medical FWFC produce around 400 images per hour, and for the Siemens X-ray is produce around 950 images per hour, and for the Philips more than 180 images per hour. For the detector size, we can see that Siemens and Philips have the same size of the detector, and the Dell Medical machine detector is a little bit larger. The pixel size of all the three X-ray machines is the same, which is 148 micrometer, and the kilovoltage range for the Dell Medical and Siemens machines are up to 100 kilovolts, and for the Philips is up to 150 kilovolt. The table dimension, we can see the difference. Almost the Siemens and Philips have the same or the near size of the table, and the Dell Medical is a smaller size table. Patient load, we can see that Dell Medical, the table of the Dell Medical X-ray machine can load 363 kilogram, and for Siemens 300 kilogram, and for the Philips 375 kilogram. So after comparing the three X-ray machines, the final selection is as follows. The primary device is Philips Healthcare Digital Diagnostic C90. And for the backups, the first backup is Siemens Multi-Impact C, and the second backup is Dell Medical FWFC. In conclusion, after we do some analysis on each specification device for the ultrasound, MRI, and X-ray, and due to the hospital requirement, we choose the primary devices as shown in the slide. In the end, I hope you enjoyed this presentation, and thank you for your time.